All right, so welcome back, everyone. It's my great pleasure to introduce Marco Freibert from University of Hamburg, who will speak to us today about left invariant generalized Einstein pairs. So please, Marco.
Yeah, thank you. Thank you for the invitation to speak here. Yeah, it was there were already three very interesting talks. One of them by Matteo, which is one of the co-authors of the paper I'm presenting today. The other one is Vicente Cortés. It's based on this arXiv article here, which is, let's say, about to be published, I think, or about to be accepted. And yeah, okay, I will. So I will start by giving you maybe a more detailed introduction into all this terminology which is relevant for the talk. I should say I'm mainly following this wonderful book by Jeffrey Streets and Mario Garcia Fernandez about generalized Ricci flow. So maybe it's a bit boring for some of you, but I mean I learned a lot from this book, and I will follow this. And afterwards I talk about our results here, and I end with some summary and outlook. So let's get started. So maybe the main motivation for introducing all these terminology comes from physics. So in physics, you have these like super symmetric field theories in 10, 11, or 12 dimensions, and in these 10-dimensional type 2 supergravity theories, you have different kinds of sectors of fields. And one of the sectors, this NS sector, which consists of bosons, which consists precisely, I mean, this is shared by all type 2 supergravity theories of a pseudo-Riemannian or Lorentzian metric, a two-form with closed free-form flux H. And I think this is the physical quantity which is interesting then, and a dilaton field, which is simply a smooth function on your manifold. And all these data can now be expressed mathematically into the following data. Namely, you can say that it gives rise to an exact current algebroid. I will explain what this is, but it's a vector field with additional structures, a generalized metric, which is an endomorphism of E, and an exact divergence operator called diff. Okay, and as usual with such field theories, you have a certain action, and then you get some equations of motion out of it. And I mean, there are more equations of motion for this sector, but the governing equation of motion can be reformulated as the vanishing of the so-called generalized Ricci curvature, which is associated to such a pair. Not only are generalized metric alone, but also this divergence operator. Okay, and then a pair satisfying this condition is called generalized Einstein. I mean, I should give you a warning. Sometimes this is, for obvious reasons, called generalized Ricci flat, and then other things are called generalized Einstein. But for the talk, this will be our definition of generalized Einstein. Okay. Okay, so what is a current algebroid? As I said, this is a vector bundle with additional structures. Additional structure, one of them is simply a bundle metric, so a non-degenerate symmetric bilinear form. This has not Riemannian signature. In our case, which the one we are studying, it has even a split signature. And then you have a bracket. So you're mapping two sections of E again to a section of E. But it's not a Lie bracket. It satisfies some kind of Jacobi identity, but it's not antisymmetric. Yeah. And you have also a map from E to Tm, a vector bundle map. This is called the anchor. Yeah. So you can make out of a section of E vector field. This will be important for some constructions. And they satisfy certain compatibility relations. And so maybe one of them, just to mention this, is that somehow in the second slot here of the bracket, you have a kind of anchored Leibniz rule. That means if you plug in f times E for a smooth function, then okay, of course, you cannot apply the other section of E to F, but you can apply pi of the other section. But this is not true in the first argument. And somehow this gives then some problems when you somehow want to construct certain tensor fields which you know of, like the torsion tensor or something. But I will come to this. Okay, good. Sorry. Okay, what one can do now is So you have this vector bundle map from E to Tm, right? Pi, and you have a the dual map is then from T star M to E star, and you can identify E star with E. So you have like these maps here, and you can show that the image of pi star is always in the kernel of pi. Okay, so it's a short sequence, and you call the Courant algebroid exact if this sequence is exact. That means, okay, the image of pi star is equal to the kernel of pi, yeah, and that pi is surjective. Okay, good. So we are only interested in these kind of Courant algebroids, and I will give you now one example, and basically these are all examples. I will explain this on the next slide. So I think this is how the generalized geometry started with, by replacing the tangent bundle by the generalized tangent bundle. So this is formally the sum of vector bundle sum of Tm and T star M. And then you have an additional closed free form, yeah? And then you can put on this generalized tangent bundle the following exact Courant algebroid structure. Yeah, so first of all, this neutral signature metric here is somehow simply you have a vector field and a one form, and a vector field and a one form. What you can do is you can plug them into each other, right? You have the natural pairing between vectors and covectors, and this can be used to define this metric. Well, this metric, so to say, is such that this decomposition here above into Tm and T star M is in fact a decomposition into two isotropic subspaces. Yeah. Later on, we will talk about certain decompositions where you have two non-degenerate subspaces, but okay, here in this case it's isotropic. And okay, this is one thing, and then you have to find this bracket, and this is called a H-twisted Dorfman bracket. So yeah, okay, you have to have a vector field part for this bracket. This is the usual Lie bracket, and then you have this one form part here. And you do not have to remember this formula precisely, but maybe you can already see that that it's not antisymmetric, because, I mean, on the one hand, you have this Lie derivative, and on the other hand, you have somehow, if you think of Cartan's magic formula, you have only one of the summands of the Lie derivative. Yeah. Okay. So this so you can spot that it's not antisymmetric. And of course, this anchor is simply the projection onto the first factor. Yeah. Okay. Good. So this is one example, or one class of examples. But basically, this is all. This is said has been proven by Cervera and Weinstein. So any exact Courant algebroid is actually isomorphic to the generalized tangent bundle endowed with all these structures. So I will put here an H to denote this dependence on H. Yeah. Okay. For some closed free form. Good, and you can say even a bit more. I mean, different closed free forms, which differ only by an exact form, they give you isomorphic exact Courant algebroids. In fact, there's a bijection between isomorphism classes of exact Courant algebroids and the third cohomology class. And the class of this here then is called the Cervera class. Or maybe I should be more precise, between small isomorphism classes. What I mean by this is, yeah, what is an isomorphism of Courant algebroids? So you want to have like a diffeomorphism of your manifold, and then a covering vector bundle isomorphism, yeah, which identifies all the stuff with the other. And small means that the diffeomorphism is in the identity component simply. Yeah. Okay. Good. So far so good. So these. So if you want to speak about Courant algebroids, exact ones, you can simply restrict to this case here, to the generalized tangent bundle. Yeah. And yeah, I mean, I mentioned also this generalized metric and divergence operator. So this will be the next thing I wanted to explain. So I'm restricting from now on simply to exact Courant algebroids. Many things can be defined analogously also for arbitrary Courant algebroids, but this will be the only thing we are interested in this talk in. So yeah, let's restrict to this. So yeah, what is a generalized pseudo-Riemannian metric? I'm leaving out the word pseudo-Riemannian, though maybe it may have non-positive signature. It's an involution, that an endomorphism which squares to the identity, such that this J tilde here. So this has been So you plug in G into one of the slots of this natural bundle metric you have on your current algebroid is symmetric and non-degenerate. And you need something additional, and pi star of T star M is a non-degenerate subbundle. Okay. Again, I should maybe say that, of course, there are some authors, for obvious reasons, there are some authors which call G tilde then a generalized metric, but I will restrict to calling the endomorphism a generalized metric. Yeah. Okay, good. So this is a generalized metric. And then next we need to define what a divergence operator is. So that's simply an R-linear map from sections of E to functions on M, which satisfies an anchored Leibniz rule. Again, if you plug in, so to say, f times E for a smooth function into the diff, then you cannot apply E to F, but you only can apply pi of E to F. Yeah. So the idea is that you always have to replace somehow Leibniz rules by anchored Leibniz rules. Yeah. Okay, but this is all. Yeah. Okay. Good. So this is the two things we are interested in. Maybe let me make a remark about these generalized metrics. Such a generalized metric gives rise to a splitting of E into E plus and E minus, where these are the plus minus eigenbundles of G. And the splitting now is orthogonal with respect to the bundle metric you have on it, the L angel R angel thing, and with respect to G tilde and also non-degenerate, of course. Then, yeah. And okay, this is the thing. Yeah, good. Okay, so we have also the splitting, and we could also start with the splitting and define pseudo-Riemannian metrics like this. But okay, okay. So yeah. So now the idea is now, okay, we can bring an exact current algebroid into this form as a generalized tangent bundle with this H-twisted Dorfman bracket. And now, okay, you have a generalized metric, and you can also bring the generalized metric into a certain nice form. Yeah. More precisely, the theorem is that for any generalized metric, you have a unique pseudo-Riemannian metric such that G, so to say, is isometric. That means, to the following generalized metric, namely of this form, yeah, on your generalized tangent bundle. So to write this down, I'm using somehow the splitting, yeah, of the generalized tangent bundle into Tm and T star M. So I'm considering now G as a map from Tm to T star M, yeah. This is how this should be interpreted. And by doing this, by bringing this onto this very nice form, I'm also singling out an H, a free form H out of its cohomology class. So, okay. So the upshot is maybe if you want to study if you want to study generalized metrics on exact current algebroids, you can simply restrict to the generalized tangent bundle with the H-twisted Dorfman bracket and metrics of this form. But you have to allow for arbitrary closed free forms. Yeah. Okay. And this will be our point of view later on. Yeah. Good. Okay. So far, so good. So now I want to say something on divergence operators again. Namely, you have this induced pseudo-Riemannian metric, right? And okay, you can use this pseudo-Riemannian metric and suppose for the moment that we are on an oriented manifold, or work locally, or work with densities instead. Yeah, but let's assume we are oriented. Then we have the volume form here of the pseudo-Riemannian metric, the classical one, and given a section of E, we can of course apply the Lie derivative of pi of E to it. Yeah. Okay, and then pointwise, this is a multiple again of the volume form. So this gives you a function, and this function is called the pseudo-Riemannian divergence. Yeah. So this is how this diff G is defined. Good. So you have, so to say, in this sense, a canonical choice of a divergence operator, and with respect to this canonical choice, you can compare other divergence operators. maybe I should have said it before. So so the set of all divergence operators is in fact an affine space, yeah, modeled on the vector space given by sections of E star, yeah. Okay. So the difference is a section of E star, yeah. And so you have some section of E, which is plugged into the first argument here, yeah. And now you call a divergence operator exact if this section of E has no vector field part, and the one form part is exact. Okay, and this is the things which are, I think, most relevant in physics. But then physicists also looked at closed divergence operators, meaning that you have a one form, but which is closed now. Yeah. Okay, this is a generalization of this. Yeah. Okay. Good. Yeah. Okay. This is somehow the background for now. And so what we have done now, we have introduced this current algebroids and generalized metrics and divergence operators, but we still have to say something about how to define a curvature. Okay, and this will be the next thing. So we should start with generalized connections somehow. Yeah. Yeah. What is the idea? The generalized connection is simply defined as a usual connection on Tm, but now we have a map from two sections of E again to a section of E. Yeah. And it should satisfy the same conditions as a usual connection on your tangent bundle. But I mean, so in the first slot, it's C infinity linear. In the second slot, you have an anchored Leibniz rule. Yeah. And so a generalized connection is such a thing. And plus you want it to preserve this natural pairing here, yeah, which you have. Maybe, I mean, as in the usual case, of course, you can somehow extend the definition of a connection on Tm to all tensor bundles of Tm, and here also to all tensor bundles of E. Yeah? So this makes sense to talk about this being parallel. Okay, this is one thing. And well, we want to have maybe want to define a Levi-Civita connection, so we should need some notion of torsion. Yeah, and so you would now write down the torsion as in the classical setting with the V bracket replaced by the bracket that we have. But yeah, the problem is that this is not tensorial, but you can add some term to make it tensorial. And so there's a natural notion of a torsion tensor. And moreover, any generalized connection induces a divergence operator. Simply, yeah, you plug in some E in the second slot, yeah, of E, and you build a trace over this anamorphism, yeah, and then you get a smooth function out of it. Okay, good. So now we define a generalized Levi-Civita connection, yeah, as in the usual setting, yeah. We call a torsion-free metric generalized connection a generalized Levi-Civita connection. Metric means that also this mathcal G is parallel. Well, this can be rephrased as that it preserves, D preserves the E plus and E minus bundles. Yeah, and okay, this is nice, but the problem is that these generalized Levi-Civita connections, they are not unique. Yeah, even if we somehow require that the induced divergence operator is some fixed divergence operator. Yeah, and this we'll do from now on. We want to have also fixing a divergence operator. Yeah. Okay. This was the situation somehow when we started our project or finished the project even also. But last year, Vicente Cortes, Markevicius, Thomas Mohop, and Oskar Schiller, I think, who will also give a talk in this series of lectures later on. They defined a canonical generalized Levi-Civita connection for any pair of a generalized metric and a divergence operator. So you could now work with this canonical one, and but yeah, okay, this is not what we did, so I will. This was just a side remark at the point. Yeah. Okay. Good. Yeah. So what you then now want to do is, of course, you want to somehow, yeah, define also a curvature as before. Yeah. So you would write this here down. Yeah, with this bracket here being the bracket that you have on E. But again, the problem is that this doesn't lead to a tensor field. The problem is that, or what you have to require is that E1 and E2 are orthogonal to each other. Yeah. Okay. So if you restrict, so to say, to E plus and E minus, or the other way around, then you get something. And the third entry doesn't have to be restricted. But in fact, if you restrict it like this, then you determine already everything you can define. So usually it's determined, it's restricted like this, and you get two generalized curvature operators. Okay, good. I should make some side remark here again. There are other approaches, for example, by Jeffrey, Strickland, Constable, and Wallach, which change the definition here a bit. And then they can define it on the entire of E star, tensor E star, tensor E star, as in the usual thing, yeah? But okay. We do not follow this here. And yeah, then you can do the same as in the usual case. You build the traces with respect to the first entry, yeah? And then you get two generalized Ricci curvature out of it, and you can combine them into one generalized Ricci curvature. And maybe I should, because I mentioned this other approaches, so the generalized curvature vanishes, but somehow the generalized Ricci curvatures, they are basically the same. There's a paper of Cavalcanti, Pedregal, and Rubio, which shows that they are the same up to some symmetrization, yeah, which if you follow this other approach. Okay, good. Yeah, good. So we now have arrived at this generalized Ricci curvature, but okay, still it depends on a choice of a generalized Levi-Civita connection, but actually in this sense it doesn't, because if you're using the same generalized metric and you want that the same divergence operator is induced, then these coincide. Yeah. So this you can show, and so you can define for any pair of a generalized metric and a divergence operator this generalized Ricci curvature. Okay. So this is well defined for any such pair. This is the upshot of all these things I wanted to tell you now. Okay, good. And then you can use it to define this generalized Einstein condition, as I told you before. So a pair of a generalized metric and a divergence operator on an X-ray current algebroid is called generalized Einstein if this generalized Ricci curvature vanishes. Good. Okay. So what happens? This is the next question. What happens if you somehow choose the Riemannian divergence? Yeah. So if you choose the Riemannian divergence operator, then you can easily show that this guy is generalized Einstein if and only if this pair here of G and H is Bismuth Ricci flat. That means the Ricci curvature of the so-called Bismuth connection, which is defined like this, vanishes. Okay, so the Bismuth connection is the unique metric connection with totally skew-symmetric torsion equal to H. And it's maybe most commonly known in complex non-Kähler geometry, because in complex non-Kähler geometry, it's one of the connections you can define which are still Hermitian. The Levi-Civita connection is not Hermitian anymore, but the Bismuth connection is Levi-Civita, is Hermitian, sorry. And there's another one, the Chern connection, which is Hermitian, and in fact you have a family connecting them, which is Hermitian. So they are much studied in this context, also for, so to say, H not being closed. But if H is closed, then you call also this geometry either pluriclosed or strong Kähler with torsion. And this is also a very interesting geometry, which has been studied. And I think, if I remember right, Beatrice mentioned also this geometry in her talk. So yeah, okay, this is somehow the connection to complex non-Kähler geometry, if you want. Okay, then these Bismuth Ricci flat things are also interesting in terms of the so-called generalized Ricci flow, which is given by this equation, because they are exactly the fixed point sets of this. I think next week James Stanfield will talk about this generalized Ricci flow on solvable Lie groups and about the results that he has with Elia and Ramiro. Okay, so something which will appear then next week again. And another comment I want to make is that this pair is Bismuth-Ritchie flat if and only if the usual Levi-Civita Ritchie, so to say, the metric Ritchie of X and X is a multiple of the norm of X hook H. So in particular, and H is not only closed but also co-closed. Yeah? And the comment I want to make here is that, so to say, this implies that the Ritchie, the usual Ritchie curvature is non-negative at least, and so manifolds tend to be compact somehow, yeah, in this context, if you want completeness. Good. Yeah, so this is something I wanted to remark. So, okay, so this is somehow the special case. So now you might wonder, give me some examples, and this is somehow the goal of the project, to construct more examples. But let me first tell you some examples which were known. I'm not claiming this is a full list. Yeah, okay, but I try to find certain examples. So first of all, take any compact semi-simple Lie group and a bi-invariant Riemannian metric on this. So such a bi-invariant Riemannian metric somehow on each simple factor, it's basically a multiple or a negative multiple of the Killing form, yeah. So these choices you have, and then you can build this this H, which is somehow the Cartan free form, yeah, associated to this, and this is even Bismuth flat, yeah. And contrary, any Bismuth flat compact simply connected manifold is like this, yeah. So these are all Bismuth flat compact simply connected manifolds, you know. And just looked at the initial reference up. Initially, this was proven by Cartan and Schouten, and then, for example, reproved by Agricola and Friedrich. And the first proof of this was exactly 100 years ago in 1926. So a very old result. Yeah. Okay, good. And due to this this thing, and for some time one didn't know any homogeneous Bismuth-Ritchie flat examples which were, I mean, one didn't know any examples which were not Bismuth flat already. So I think Jeffrey and Mario asked in their book the question if some result similar to Aleksievsky-Kimmelfeld should hold. And Aleksievsky-Kimmelfeld says that in Ritchie flat Riemannian homogeneous manifold is actually flat, but in the Bismuth case, this is not true. And the first counterexamples were given, yeah, I don't know how many years ago, maybe 3 or 4 years ago, by Podesta and Raffaello, and they had another paper where they have more examples, I think infinitely many then. And another class of examples of Bismuth-Ritchie flat again, homogeneous ones, have been constructed by Jorge Lauret and Cynthia Will on, or they constructed basically examples on any so-called aligned compact homogeneous spaces with 2 simple factors. So under some mild assumptions. So
sorry, can you say what does aligned mean here?
Yeah, okay. Yeah.
Or, well, it's okay. I don't know.
Yeah. So G is a product of 2 simple Lie groups, yeah, and K is a compact subgroup. And one way of rephrasing this is that, or in general, if you have also more factors, that somehow the third Betti number is maximal. That means it's equal to S minus 1 if S is the number of simple factors, but you can rephrase it very easily into an algebraic condition, which somehow says that this K is embedded into each factor in a certain uniform way. I think say that. And this, I think this makes computations easier. So yeah, this is the idea. And I think that they, Jorge and Cynthia, they also studied the usual Einstein metrics on these spaces and found examples. So I think that's a very interesting class of homogeneous spaces which one can study. Yeah? Okay. But yeah, okay, good, thank you. So this for somehow the Bismuth-Ritchie flat Riemannian case. But now now we leave the space of the Bismuth case and the Riemannian case, namely Vicente has a paper with David Kusche. I think it was basically his PhD thesis where they classified all left invariant generalized pairs on three-dimensional Lie groups with arbitrary signature. So you can have Riemannian or Lorentzian. I mean, the signature is the one of the underlying pseudo-Riemannian metric, I should have said, yeah, and arbitrary divergence operators. Okay, so this was their paper. So many more examples outside of this Bismuth-Ritchie flat case, yeah. And somehow our goal is now to construct more of these examples, yeah. So this is the thing. So I'm setting the stage a bit. Yeah, I have a Lie group, and I take as E now really the direct sum of the Lie algebra and its dual, yeah. And then I identify a left invariant thing. So you have a left invariant exact current algebroid, a left invariant generalized metric, and a left invariant divergence operator with a triple consisting of this closed free form on your Lie algebra, an endomorphism of this form, special form here, determined by a pseudo-Riemannian metric on your Lie algebra, and a divergence operator which can be identified with an element E star because it's left invariant. Okay, what I'm doing implicitly here is that somehow I'm fixing another divergence operator, namely the one which is 0 on all left invariant sections, yeah. And I'm comparing with this now, yeah. This is how I can somehow identify the divergence operator now with a vector space. And what is this somehow fixed 0? I mean, it's not 0 everywhere, yeah, but only on left invariant things. This is in the unimodular case, it is the Riemannian divergence operator. Otherwise, it's a bit different. But in the unimodular case, it's the divergence operator, the Riemannian divergence operator. Okay, good. So we are working now with this triple here, yeah. Okay, good. So and then yeah, Vicente and David Krusche, they had some formulas also for these generalized curvatures. The first thing, I mean, was now to somehow rewrite these formulas maybe in a more adaptable way. At least we were more successful with these formulas. I mean, basically the same formulas, but we say that H, G, and diff is a generalized Einstein if and only if these four equations hold. So you should not remember all the equations, but I will tell you a bit about this. Yeah. First of all, maybe what is at star of X? So this should be interpreted as follows. So you're taking at star of X, you apply it to Y, so it's an endomorphism. You apply it to Y, and this is at Y, and then the adjoint of it, so to say. So maybe I should call it transpose, yeah, to distinguish it from the adjoint operator here. So it's the transpose of this adjoint operator and acting on X, yeah. Okay, and maybe I should point out if this is 0, yeah, this will be the case and now, then what happens? Then the first equation, the left-hand side vanishes, and then on the second equation, on the right-hand side, also this minus term vanishes. So you have two terms with a plus in front. So if you are in the Riemannian setting, this gives you that these guys are 0, yeah. So at XS, by the way, maybe it's also important to say this, it's the symmetric part of the adjoint operator. So at X is simply the Lie bracket with X, yeah, if this was not clear. And another thing which we study is that if things only for divergence equal to 0 in the Lorentzian case, and then you can see that the last two equations are automatically fulfilled and the first two also simplify a lot, yeah. Okay, just to motivate why we are studying certain cases, which will now appear. Okay, the first thing is in the Riemannian setting where we have some results, and this is the following. So we have some kind of reduction result to the commutator ideal. So G prime is the commutator ideal, yeah. So we are in the Riemannian setting, and such a quadruple then is generalized Einstein if and only if the following three conditions are fulfilled. The third one is saying that some of the restrictions are generalized Einstein, yeah, but there are more conditions. So first of all, the orthogonal complement, yeah, this is an abelian subalgebra which acts skew on G prime, and from this you get that G is actually such a semi-direct product, yeah. And then you have more equations. You have an equation for the divergence operators, and you also have that somehow H restricts to a form on G prime actually, yeah. So if you plug in elements of H, then this is 0. Okay, good. So somehow the upshot is, and I will explain this now. So this gives you a classification of solvable generalized Einstein Lie algebras, which is not interesting. I will come to this. And basically somehow says that the only interesting part is maybe the semi-simple part somehow. But I will.
All right. What exactly is the meaning in part two? What is this superscript B?
This is okay. I mean, it should be flat. Yeah. So, yeah.
Oh, yeah.
Yeah. Maybe I should have used flat instead of B. Yeah.
No, I understand. Yeah. Okay. Thank you.
So it's the dual part, right? Exactly. Good. Yeah. So as I said, I will come to now implications for the nilpotent and solvable. I mean, first of all, nilpotent situation and then solvable situation. And I will maybe tell you at the end some. I mean, it would be somehow nice to see some more general picture behind this. Yeah, I do not know how to interpret this. I mean, I will give you some interpretation or some possible interpretation at the end, which would be interesting. But let's state it for the moment as it is. And use it to, first we want to look into the proof a bit, sorry. So first of all, yeah, I say that at star of X is 0 if I choose X in this orthogonal complement. So why? This is very easy. I mean, this is by definition, so to say. At star X applied to Y is this guy, at Y transpose applied to X. So by definition, this is at Y set with X, yeah, this is just a definition of the transpose, but this is the Lie bracket, and X was orthogonal to Lie brackets, so this is 0, yeah, and as I said, this directly implies that the first equation reduces to this equation here, and so that somehow at X as a 0, the symmetric parts are 0, and X inserted to H is 0, yeah, for X in H, yeah. Okay, now somehow, okay, this is the upshot, and now this at xs equal to 0 means that at x is a skew symmetric operation, so it acts skew symmetric on the commutator ideal, and it also tells you that H is abelian if you look a bit closer. Yeah, so this is some of the conditions then. And well, I mean, the other ones are more involved, a bit more involved. So I will not bring them here, but two other equations somehow directly yield this equation then. And then you can see with a little bit of work that somehow the other equations then reduce to the generalized Einstein condition on the commutator ideal. So yeah, okay, good. So this is somehow the proof how it goes. Yeah. Okay, and now I want to talk about some implications then. First of all, the following implication for the nilpotent. So nilpotent is the important word here, yeah. So if you have a nilpotent generalized Riemannian Einstein Lie algebra, then it has to be abelian and H has to be 0, yeah. So it's I mean, the divergence operator is arbitrary, but yeah, the other ones are very restrictive, of course. And how does this proceed? This is very easy to deduce from this. So first of all, the reduction result gives you that, I mean, as I said, this is a symmetric product, but with an abelian factor, and this abelian factor acts as Q on G prime, yeah? And H lives on G prime as well, okay? And we now want to show that G prime is 0. Yeah, so now, I mean, this is a very classical result. Engel theorem tells you that adjoint operators in nilpotent Lie algebras act nilpotently, so RK acts nilpotently also, and so it has to act trivially, yeah. So what we get is that we really have a direct sum as Lie algebras here, G prime and RK, yeah, okay. And now, because it's nilpotent, this is only possible if G prime is 0. Because, I mean, what you get from this is that somehow the commutator of G prime is again G prime, and this is only possible if G prime is 0. So G is abelian in H because it lives on G prime is also 0, yeah, okay. So really, there are no really interesting nilpotent Lie algebras in the Riemannian setting. Yeah, there are some in the Lorentzian setting, I should already say, but not in the Riemannian setting. Okay, let's come to a slightly more general class, maybe the solvable class. But somehow there you also get not much more. So what is, I mean, this is also a very basic result in Lie theory that Lie algebra is solvable if and only if its commutator ideal is nilpotent. So what you can do now is you can apply this reduction result to say, okay, the G prime has to be generalized Einstein, and so G prime has to be abelian, yeah, and H has to vanish on this as well. So what we get in the end is that such a solvable Lie algebra is generalized Einstein if and only if it's a semi-direct product of Rm with Rk with two abelian factors, where Rk acts skew on Rm, H is 0, and yeah, you get also this equation for the divergence operators. And I mean, maybe you surely know this very famous paper by Milner, where he, amongst other things, determined the flat Lie algebras, and this is exactly the class of flat Lie algebra. So you have a classically flat Lie algebra also. So in this sense, it's somehow not very interesting, yeah. But I mean, it's nice to have this result. Yeah. Okay.
Marco.
Yeah.
Marco. For generalized Einstein with divergence, you still have that Ricci is non-negative, right?
Yeah, this I wasn't sure when I was preparing this. Yeah, that's a good question.
Because these two corollaries would follow directly from Ricci, non-negative.
Yeah, I know from the Milner paper, right? I mean, I was also thinking about this, if this is clear or not. I do not think so, but maybe I'm misleading. Maybe then it would also directly follow from this, yeah.
Well, yeah, I think the divergence operator is not the standard one. It's definitely not an immediate consequence, I don't think. But
yeah. Okay, that's good to know, because I was asking by preparing, I was asking exactly this question, but I didn't get far. So yeah, as Jorge said, if you had a Bismuth-Ricci flat case, this follows from the paper of Milner, because he also has these that it's non-negative, yeah, yeah, that's right, yeah, that's right. Okay, so it doesn't follow from this result, but it's maybe some generalization of this in a certain sense, yeah. Okay, good. Yeah. So this was all I wanted to say to the Riemannian case somehow. Then let's go to the Lorentzian case, which, as I said, is maybe also still interesting for physicists at least. I should mention this. I mean, we also get a, so to say, a full classification in the four-dimensional case, but this is also not very deep, because what you get is you only have two solvable Lie algebras, namely the abelian one and R acting non-trivially on R2 by skew symmetrically, and then SO3 plus R is the third case. But these are all Lie algebras which can emit such structures, and we can determine all structures, but okay, they're not that many. Yeah. Good. So there are more, like in the Lorentzian case, and in the Lorentzian case, we looked, for example, at the so-called almost abelian case. So what is an almost abelian Lie algebra? It's a Lie algebra which has a codimension 1 abelian ideal. I usually call it U. When I worked a bit on these Lie algebras. And so the entire Lie bracket is encoded into, so to say, one endomorphism, yeah, of U. So you're taking any X which is not in U, and you build the adjoint operator and restrict it to U. So in the end, you have such a semi-direct product, yeah. So Rn minus 1 F acting on Rn minus 1 by this. Okay, this seems to be a very restrictive class, but still, I think it's a very interesting class. It has been studied much in the last years, because of course it's highly accessible, but also because, for example, some low-dimensional manifolds, compact manifolds, are almost abelian solved manifolds, like, for example, primary Kodaira surfaces. So in particular, the Kodaira-Thurston manifold is one example, yeah. And also the example, so to say, by Marisa Fernandez. Marisa Fernandez found the first example of a closed T2 structure on a compact manifold where there is no torsion-free T2 structure. This was also an almost abelian solved manifold, so a compact quotient of such a Lie group. So I think they are interesting to study. So we studied this case in the Lorentzian setting. And what we obtained is somehow, in a certain sense, almost a full classification under the additional assumption that the divergence operator is 0. Yeah, so somehow we are the the Lorentzian Bismuth-Ritchie flat case somehow. And under a certain additional assumption, namely, if H is non-zero and the codimension 1 ideal is Lorentzian, I mean, it may also be Riemannian or degenerate, but if it's Lorentzian, then we need to assume that f of S, so the symmetric part of this f, has no non-real eigenvalues. So please note, on a Lorentzian vector space, of course, you do not have the spectral theorem. So there are other types of normal forms. One, of course, the diagonal one, as in the spectral theorem. But there are other ones, and there is one particular which has non-real eigenvalues. Okay, good. So this seems to be too technical, but the other ones we have achieved, and many of the examples have H equal to 0, but there are also some examples with H non equal to 0 in arbitrary dimensions, as I said. Let me maybe give you some comments on how to prove this. Yeah. I mean, I had this proposition with these 4 equations, and in the case divergence equal to 0, this reduces to 2 equations, and then you can somehow solve them by hand if you want. And what you have to use is the normal forms of symmetric endomorphisms on Lorentzian vector spaces. And as I said, there's one normal form with non-real eigenvalues, which causes some troubles. Yeah.
Sorry, Marco. When you say div equals 0, it means it's like the Riemannian divergence, or the...
Yeah, no, not all exactly in the unimodular case. It's the Riemannian divergence. Yeah, this corresponds to this. Otherwise, it's equal to the trace form, so to say, or minus the trace form. Yeah. But in the unimodular case, which is maybe the most interesting, it's the Riemannian divergence. Yeah. So div equals 0 means that it's 0 on left invariant sections, so to say.
Oh, okay.
Mm-hmm. This is the meaning. Yeah, good. Yeah, exactly. So we are using this a lot. I should also say that one can extend the results also slightly to the case divergence non-equal to 0. But yeah, full classification is only in divergence equal 0 case. And yeah, for example, in the very special case that H is also equal to 0, so we are talking about classically Ritchie flat things then, and non-degenerate codimension 1 abelian ideal. Just to give you an impression what kind of equations you have to solve, you can see that the generalized Einstein condition is equivalent to f being normal, and the trace of the symmetric part, square of the symmetric part, has to be 0. So okay, so this is a linear algebra problem then. Yeah. Okay. And okay, this is maybe only a side remark, which I found still interesting. So I mean, so yeah, simply restrict to the. I mean, I only talked about Lorentzian signatures now, but what happens if you go to higher signatures? And I think this gets then even more complicated, because what we can prove is if you are on Rn, then we cannot have a Lorentzian Einstein generalized metric with divergence operator 0, but H non equals 0, yeah? And the same is also for split signature in 4 dimensions, but in 5 dimensions, there's such an example of signature 2-free. So it gets, I think, even more complicated if you have other signatures, yeah? Just to see that I think the problem is maybe with higher signatures is even more complicated then. Good. Okay, so this is one thing we were able to prove, and then the last thing what we were able to prove is in the 4-dimensional case, but again under the assumption that the divergence operates 0, and again we have some slight extensions to non-zero, but mainly we have divergence equal to 0. We have a full classification under 2 additional assumptions, or under one of the 2 additional assumptions. Either you assume that G prime is non-degenerate, or that G is almost abelian. So in the 4-dimensional case, you can solve the almost abelian case completely. This is what I'm saying. Otherwise, to get some classification, you have to assume that the commutator ideal is non-degenerate. Okay. Otherwise, it gets really complicated. Yeah. Good. So yeah, this was somehow the content. So let me summarize what I've said, and then maybe give you an outlook about other results, about future things. So we had this general reduction result that I mentioned for the generalized Einstein condition to the commutator ideal, plus is such a semi-direct product with RK acting skew symmetrically on G prime. In fact, what it says it says it's locally a Riemannian product. by the way, I should have said this, and more restrictions here. And this restriction result that implied that somehow the solvable generalized Einstein cases in the Riemannian setting are not interesting because they are flat, yeah, and H is equal to 0. And we had a full classification in 4 dimensions, and in the Lorentzian case, with divergence equal to 0, we almost had a full classification in the case that G is almost abelian. And in 4 dimensions, we had full classifications in the almost abelian case, and or if G prime is non-degenerate. Yeah. And what is maybe nice, we now have plenty of explicit examples in these dimensions, yeah, which may be interesting for physicists. Okay, good. So what is maybe interesting now to study? So maybe let me mention 2 things. The first thing is, as I said, somehow the full equations of motion are not only the generalized Ricci curvature vanishing, but also the so-called generalized scalar curvature vanishing. Yeah, and maybe you want to assume that the divergence is a closed divergence operator. Maybe I will not go into too deep into the definition of this scalar curvature, but just say that it's not a trace of the Ricci curvature. So these are independent quantities, yeah. And I think the initial way to define this was via a certain kind of Lichner-Rovitz type formula, but there are now new approaches using these other definitions of this generalized curvatures, yeah. But okay, it's independent. That's important, yeah. Okay, so the idea is now maybe to look for solutions of both equations, yeah. And there's an ongoing master's project of Michael Kinne under the guidance of the center, which looks into our generalized Einstein pairs and tries to find those which are scalar flat, yeah. And as far as I understood, he already has a full result in 4 dimensions and also some Lorentzian examples with divergence not equal to 0. And in the Riemannian case, somehow in the solvable world, this even then also forces that I think the divergences operators are 0, meaning that they are the Riemannian divergence, yeah. And but in the Lorentzian case, he has some non-trivial explicit solutions of the equations of motion, yeah. That's maybe very interesting. And yeah, I think our idea is maybe to search for homogeneous generalized Einstein pairs or full solutions on other types of homogeneous manifolds. So for example, of course, compact semi-simple Lie groups would be interesting. Maybe I should mention that Jorge and Cynthia, they also proved a certain rigidity result. So we had this Bismuth flat things, yeah, with biomimetic and the Cartan freeform, yeah. And if you change one of them, yeah, then you do not get new solutions to the generalized Einstein condition. That's what they proved. So yeah, it's an open question if there are any other generalized Einstein metrics at all, Bismuth flat or even with divergences, yeah. And then also these aligned compact homogeneous spaces are surely interesting. Okay, this would be maybe the natural things to start with, I think. But we didn't start so far. Let me end with some idea maybe for interpreting this reduction result. So I mean, what we can do is we can somehow consider so G to G modulo G prime. This is abelian. So you can consider this as a Riemannian submersion, yeah, with fibers being the commutator ideal. Okay, and and for such situations, and if you fix the Riemannian divergence operator, so you're talking about Bismuth-Ricci flat things, then this fits into the following. I mean, it's a really mainly an observation. It follows directly from O'Neill's formulas. So what is the situation? So start with a Riemannian submersion and a Ricci flat basis, and you have the mean curvature vector here, and you want that somehow if you differentiate along horizontal vector fields, it should not be horizontal, yeah? This means this here. So a certain condition, and this is satisfied in our case, and add some closed freeform, and then somehow the total space is Bismuth-Ricci flat if and only if, yeah, both O'Neill tensors vanish, yeah. So A was, just to remind you, was the obstruction against integrability of the horizontal distribution, and T was basically the fundamental, second fundamental form. So if it's 0, it's a totally geodesic thing. And again, this both vanishing implies it's locally a Riemannian product, so not very interesting. You get also that if you plug in horizontal things into H, this is 0, so it reduces to a form on the fibers, and all fibers are rigid flat. So this is an if and only if here. Yeah. So this is somehow a kind of reduction result, which in which our case for Riemannian divergence is contained in. And the idea would, of course, be maybe somehow to generalize this. And I think for this, you first have to define a theory of generalized Riemannian submersion. Yeah. And then maybe the idea would be to find such a general reduction result, which has our reduction result as a special case. Maybe the last sentence I want to say is that there has recently been developed by Oscar Schiller and Vicente Cortés a theory of generalized Riemannian immersions. Yeah, I think Oscar will talk about this in a few weeks. Yeah, and of course this will be very helpful for such a goal. But again, we have not started. This is just an idea of how to generalize also this reduction result. And I think independent of this reduction result, maybe such a theory would be very interesting. Yeah. Okay. So yeah, this was all I wanted to say. So thank you for listening.
Yeah, thank you. All right, so yeah, are there any questions?
I have one question. Is there any known example in signature to 4?
Not that I know of, no. But I would guess that there are many examples, maybe even on abelian Lie algebras, yeah, as I said, with H non equal to 0, but I didn't try to find it, and I do not know of any, yeah.
Yeah, because there's some there's a paper by Alexevsky and others studying nearly pseudo-Kähler metrics, and there is one interesting solvable example, signature to 4, which is nearly pseudo-Kähler, but no, it is not pseudo-Kähler. But I don't know about the generalized Einstein condition.
Oh yeah, okay. No, I do not know of this example, but maybe it would be interesting to look at this. Yeah, yeah. Yeah, thanks for pointing out.
Okay, thanks.
Could you go back to the classification of the 4D Riemannian?
Oh, sorry, yeah, of course.
Signature.
You mean in the Riemannian signature, yeah?
Yeah,
yeah. You mean this one or the other one? What I said about?
I can't see it anymore.
You mean this remark or? Sorry,
no, I mean I think you stopped sharing, if I'm not mistaken.
Ah, sorry. Yeah. Okay. Thank you for pointing out. So I should. Yeah. Okay. Thank you. So. Okay. So now, yeah. So you mean this remark or this reduction result, which I had before?
I thought in the summary at the end, you were saying there was a classification of the left invariant.
So maybe I go to this. Yeah. So, okay.
What is the full classification in 4 dimensions? Do you just mean in the solvable case?
No, in all cases, but I mean there are only 2 non-solvable Lie algebras in this case. I mean full classification on this left invariant setting, of course, and there are only SO3 plus R and SL or SO21 if you want plus R, which are non-solvable. So and you can deal with them. I mean.
And does the last one have compact quotients? Or maybe not.
It's a good question. I mean, that's a good question. I do not know. Yeah, at the moment.
And I guess in what is the divergence operator for those? Is it the Riemannian one, or?
I think you can choose more for the generalized Einstein condition on SO3. I mean, SO21 plus R doesn't have one Riemannian, so maybe I should say this. So in this sense, it doesn't matter. But SO3 plus R, you can have more divergence operators. We have a thing, but okay. But if you're thinking about, I mean, I think I forgot to mention this. If you want full solutions of the equations of motion, then you have less possibilities. I think Michael Kinne showed that practically only the example you have in this generalized Ricci flow paper is the only example of on SO3 plus R. I think you're considering this at some point.
You mean if you further impose scalar flat?
Yeah. But then you can have something divergence, I think, acting on this R part, so to say, only. But I think if you're only imposing generalized Einstein, you have a bit more. Yeah. I do not remember exactly the conditions, but you have more.
Okay. Yeah. Thank you.
Yeah.
Any others? Okay, if not, yeah, let's thank Marco again for the nice talk.
Yeah, thank you.